we're going to start graphing rational functions. A rational function is a quotient of two polynomials. Discontinuities of rational functions are all caused by division by zero. That is the good news. The bad news is that there are more than one type of discontinuities. Let's see what those are. Consider the functions f of x equals 1 over x and g of x equals x over x. There are similarities. For example, f and g have the same domain. Basically, x cannot be 0 because x is in the denominator in both expressions. But they don't behave quite the same. Let us imagine that x is a very small number. It's really tiny. As a decimal, it would look like 0.000001. It would have a lot of 0 before a 1 or any other digit. As a fraction, it would look like 1 over 10 million. And visually, it would look like we could barely see it apart from 0 on the x-axis. This is 1, this is half, this is a tenth, and the closer we get to 0, the smaller the number is. Imagine that x is so small. What would be the reciprocal of such a small number? Well, you can use the calculator. What would you get if you punched in 1 divided 0.000001? Or what do we have to multiply 1 over million to get to 1? A number and its reciprocal multiplied to 1. So if you're thinking of x as 1 over 10 million, then the reciprocal has to be 10 million. So what that does is that if x is 1, the reciprocal is 1. If x is 1/2, the reciprocal is 2. If x is 1/3, the reciprocal is 3. If x is 1/4, the reciprocal is 4. And you see there is some sort of a strange pattern going on. And if you want to ask, well, will the y get as high as 10? Then the answer is yeah, it will do when x is 1 over 10. Visually, as we would on the x-axis approach 0, that is the same algebraically that we're taking tinier and tinier positive numbers for x. And visually, you would see this crazy behavior, and algebraically, the numbers would be very large. Pretty much the same story on the negative side. So the reciprocal of -1 is -1. The reciprocal of -3 is -3, and so on. So you get these very large numbers. Let us look at g of x equals x over x. Again, x cannot be 0. But what about a tiny number x? Well, as long as x is not 0, even if it's outrageously small, if you divide it by itself, you get 1. Yeah, I don't want to mess this up. So we could just say, well, let's simplify this as 1. This is what my algebra teacher taught me. Well, the algebra teachers didn't tell you the whole truth. Because the whole truth is, if you have two functions, f and g, the two functions are equal if and only if f and g have the same assignment and the same domain. So as functions, these two sides have different domains, right? This is a perfect domain, but this one doesn't. This one does not allow x to be 0. As functions, these two are not equal to each other. So this equal sign we really didn't have the right to use it here. If we want to be really precise, this is what we can say. X over x is, well, if x is 0, we have undefined, right? And if x is not 0, then you have a non-zero number dividing itself, that's 1. This is how we can simplify between functions as opposed to just expressions. So the graph would be the constant horizontal line 1, but that's not quite right. We should sort of indicate that something weird is going on at x equals 0. So we just indicate with a little circle that this one point is not part of the graph. That's what we call a hole. This is what we call a vertical asymptote. So these are the two types of discontinuities of a rational function, a vertical asymptote, and this one is a hole. This is also called removable discontinuity because this function is almost continuous. It's more like someone took a continuous function, the constant 1, and then messed it up by taking out a point. So a removable discontinuity means that we could smartly define a point that would stitch up the function to be continuous. In this case, that point is obvious. It's the one that we just artificially put out. So this scenario occurs in situations where you don't have this kind of forced algebraic situation. Okay. This one is called unremovable discontinuity, because obviously you cannot define a function value for x equals 0 to make this function continuous. There is this huge irreconcilable break between the two parts of the function. So what is common is that 0 is not part of the domain. What is different is how the neighborhood of 0 behaves. The neighborhood of 0 is just an interval containing 0. Here, an interval around 0. Well, we know how 0 behaves, but every other number, you just cancel it out to 1. Here, the smaller the number, the greater reciprocal is, right? So the neighborhood of 0 causes this really strange behavior. This is a discontinuity that cannot be fixed. Later on in calculus, you will see that the idea of continuity is that if you have two numbers on the x-axis that are close to each other, then whatever you assign to them, they're going to be, the function values will be close to each other. And this is what breaks down here, because if you take a tiny negative and a tiny positive numbers, they're very, very close to each other, but then their reciprocals are mapped to a very large positive and a very large negative number. So that's why the discontinuity is caused here. So these are the two types of discontinuities that rational functions have. The question is now, how can we tell the difference? Vertical asymptotes are caused by division by the neighborhood of 0. Those are really, really large numbers. So, for example, if x equals 3 is a vertical asymptote, then x minus 3 is a factor of the denominator. So how can we tell what is a vertical asymptote and what is a whole? Let's just review what causes a vertical asymptote. So a vertical asymptote is caused by division by the neighborhood of 0. Not quite 0, just the neighborhood of it. That means that we have really, really, really tiny numbers in the denominator that are not balanced out by the same tiny, tiny number in the numerator. So it's basically a genuinely small number in the denominator that is not in the numerator. So that's a vertical asymptote. Now let's look at these expressions. So 1 over x, we just went over that this is a vertical asymptote, right? Now what about this one? We can't tell right away whether it's a whole or a vertical asymptote. So let's just simplify it. We have two options here. We can say x over x squared equals to 1 over x. Or we can say x over x squared equals to 1 over x if x is not 0 and undefined if x is 0. So which one should we use? This is correct, right? X over x squared, when we simplify it, then it's 1 over x, and that's always the case as long as x is not 0. And if x equals 0, then we're dividing by 0, so the expression is undefined. So this is correct. But this here is sort of unnecessary, because if you compare the two denominators here, without mentioning x equals 0, they are the same, right? The domain of this is x cannot be 0, and the domain of this x cannot be 0. So, yes, we are allowed to do this, but we actually don't have to, because the formula itself still reminds us that x cannot be 0. So that information needs not to be expressed separately. So in this case, this is really 1 over x, and so it's the same graph, right? It's a vertical asymptote. Now let's look at the next one, x squared over x squared. These are our two options. Is this correct? The first one is clearly not correct, because if you forget where this one came from, that would be defined at x equals 0, but this isn't. So now, because this formula has no issues at x equals 0, we have to remind ourselves when we simplify, right? And why do we have to remind ourselves? Because it disappears from the denominator. We're going to have to use this. So x squared over x squared is 1 if x is not 0, and undefined if x equals to 0. That's a whole, because you either have no value or just 1. You don't have those crazy big numbers. Why? Because after simplification, there is no teeny tiny number left in the denominator to create that crazy vertical asymptote situation. So this one is a whole, and the graph would look just like x over x looked. It's almost the line constant 1, except for at x equals 0. Okay, so let's see the next one, x squared over x. We could have two options. If we look at this, the domains become different. The right hand side is okay with 0, the left hand side isn't, which means we must go with this format. So this one here is x when x is not 0 and undefined when x is 0. And the way we graph that, we graph y equals x, which looks like this, but then not at 0. And so that's a hole 2. Now what happened here? Why did we get these holes? We got these holes because we didn't get a vertical asymptote. That is to say, we ran out of unbalanced tiny numbers in the denominator. In this case, after the simplification, there was still a factor in the denominator that caused trouble at its 0. Here no, here no. So we have a vertical asymptote when the linear factor that takes the 0 in the denominator is still in the denominator after cancellation. So a vertical asymptote is caused by a factor in the denominator even after the cancellation. We have a hole where we don't have a vertical asymptote. That is to say that we run out of those tiny numbers, tiny troublemaker numbers in the denominator. That means that in case of a hole, the 0 disappears after the cancellation. So a hole is a factor of the denominator only before cancellation and not after. And just a side note, that is completely independent. What happens in the numerator is just what happens in the denominator determines this. So discontinuous of the rational function, find the zeros of the denominator. Those are all discontinuities. Then cancel out. And whatever stuck around in the denominator is vertical asymptote. Whatever disappeared from the denominator is a hole. That's it.